Hi, Trig. Here we are, 4-6. We just learned about graphing tangent. We still need some practice and seasoning, I'm sure, but we're going to keep moving on. We're going to keep practicing as we go. We'll keep spiraling and coming back and hitting it. So we need the other graphs. We haven't graphed cotangent, we haven't graphed secant and cosecant, so that's what we're going to hit today. As you can imagine, hopefully, tangent and cotangent are pretty similar. And even starting at how I'm going to show you guys what it looks like is pretty similar. So without further ado, let's go ahead and look at it. To graph one period to start with, we're just going to go around the unit circle, right? This is where we started tangent, so let's start this on cotangent. We have to remember, though, that the definition for cotangent, that ratio, is going to be the x-coordinate over the y-coordinate. So at 0, the x-coordinate over the y-coordinate is undefined. 1 over 0, no good. There actually is going to be an asymptote right there at 0. As we move up to pi over 2, x over y, that's 0. 0 over 1 is just 0. So asymptote, 0, probably an asymptote. Let's see. X over y, yes. We can't do negative 1 divided by 0. So asymptote, probably a 0 if we're following this pattern. 0 over negative 1, yeah, the x over the y is 0. And then back to 2 pi, we get another asymptote. So we get 3 asymptotes going around the circle one full time on this one. Asymptote, 0, asymptote, 0, asymptote. Well, let's put all this information down. Let's actually put this on our graph and see what we have. So here we go. This is what it looks like. Not too bad. We need those quarter points now. So halfway between 0 and pi over 2 would be pi over 4. I need to plug a pi over 4 in there. Okay, so I would draw a triangle. Pi over 4 is 45 degrees. The sides would be 1, 1, square root of 2. The cotangent is the adjacent over the opposite. Right? Tangent is opposite over adjacent. Cotangent is adjacent over opposite. It would still be 1 over 1. So if I plug a pi over 4 into my function up here, right here, if I plug pi over 4 in, I'm going to get 1. So pi over 4 would be right here. I would go up to positive 1, and I would put a dot. From there, the rest of the dominoes start to fall, just like tangent. As it approaches one side, going up, it approaches the other side, going down, that sort of thing. So let's see, pi over 4, it was a positive 1, which would mean at 5 pi over 4, it's going to be a negative 1, and it is. If it rises on one side of my 0, it's going to fall on the other. If it falls on one side of a vertical asymptote, then it rises on the other, and so on and so forth. That's 2 full periods of cotangent right there. So it looks pretty similar. Hopefully you can kind of spot the differences, where the asymptotes are different. The general shape looks like it's been reflected, right? It's been reflected upside down instead of going up as we go to the right. It actually goes down as we go to the right, but they're pretty similar. Okay, let's talk the biggest change here. To graph tangent. Okay, the first thing we should be doing is finding 2 consecutive asymptotes, not finding the period. That was sine and cosine. For tangent, we set the argument equal to pi over 2, and we set it equal to negative pi over 2. That will give me 2 consecutive asymptotes. Then we can find the quarter points. Then we can start letting the dominoes fall. For cotangent now, we set the argument equal to 0 and pi, because that's where asymptotes are for cotangent. There's not asymptotes at pi over 2 and negative pi over 2 for cotangent. We just saw that. We went around the circle. We got asymptotes at 0, pi, 2 pi, 3 pi, but we just want 2 consecutive ones. So we'll use these 2. We'll solve these little equations and get where my asymptotes are. Okay? That's it. There'll be plenty of practice for you, but we are going to move on. We've done cotangent. Check it off the list. Now we want to do cosecant. There's our next reciprocal function. Remember, these are all reciprocal functions for our normal guys. So same process. I would want to go around the unit circle one time. Let's check those key values and see what's happening from there. So we have to remember at cosecant, for cosecant, we are 1 over the y-coordinate. Sine is the y-coordinate. Cosecant is 1 over sine. So cosecant is 1 over the y-coordinate. As we go around, 1 over the y-coordinate. 1 over the y-coordinate. No good. There's going to be vertical asymptotes on these as well. Okay. 1 over the y-coordinate. Just 1. 1 over the y-coordinate. Asymptote. 1 over the y-coordinate. Negative 1. 1 over the y-coordinate. Another asymptote. So kind of the same process. It's going to look kind of similar to what we were doing before, but there will be a difference, and let's check and see what it is. So here's the information we just talked about. Went around the circle. I got my asymptotes, 1s and negative 1. Now it's something like this. Well, if we're all talking like the same lines of tangent and cotangent, which we should, vertical asymptotes in general, I know my graph has to go through this point and has to approach this vertical asymptote either going up or going down. We just need to figure out which one. So I probably need to figure out what point that is and plug it in. Same thing here. This is pi over 4. Probably going to plug in pi over 4 and figure out, does it go up or does it go down? Okay, so this one would be pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. If we find those quarter points, we can kind of figure out what's going on, okay? We'll let the dominoes fall. Well, this is not, these aren't the easy ones, right? If I was going to do pi over 4, so we want to find the cosecant of pi over 4, which we are all capable of. Pi over 4 is in the first quadrant. Looks like that. It's a 1, 1, square root of 2. Sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. Okay, well, the hypotenuse over the opposite, that's going to be the square root of 2. It's not a clean one, but hey, it is what it is. We are in trig and pre-calc. We can handle that. Square root of 2 is like 1.4 something. I'm checking it, but I am. Yeah, 1.414. So we know that if I go to pi over 4, it's going to be a little bit more than 1. It's going to be up here somewhere. Okay. If I did 3 pi over 4, okay, 3 pi over 4 is right here. It's going to be positive square root of 2 again. 1, 1, square root of 2, hypotenuse over opposite. So it's going to be a positive square root of 2, positive square root of 2, because that's where sine's positive. That's where cosecant is going to be positive. Negative square root of 2, negative square root of 2. That's where sine's negative, so cosecant is negative. So let's put all that information down on our graph, and it should look like this. So there were those pi over 4s. Those were those quarter points. We're talking about this one, this one, this one, and this one. Square root of 2 about 1.41. A little bit more than 1. All right, so now we just kind of play connect the dots. There is a line right here. Let's add it for future generations of trig students. All right, there was an asymptote at 0, so let's put it so you can see it. I tried to offset it. There we go. Okay, so now let's be detectives here. My graph has to go through this point, has to go through this point, has to go through this point, and then has to approach this line but never quite get there. Okay, it's going to look like a parabola. It's going to come down, hit this, and approach that without bound. Same thing here. Approach this. It's kind of going to look like parabolas. They're not parabolas. Parabolas go left and right forever, and these are bounded by these vertical asymptotes, but it definitely has that sort of shape. So this would be one period, one time around the circle, for y equals the cosecant of x. Pretty crazy looking. I had a student once call it the crazy circus, because it's CSC. I don't know why that stuck with me. I know there isn't even an S in crazy, but it's crazy looking. They're definitely different. Okay, so I promised you guys when we graph these, if you follow me and follow this prescription, you would not have to graph things like 1.4 and the square roots of 2. You can handle it. We already proved that. But yes, like a lot of things, there are tricks. And if you did the bell work, then you've already kind of handled the trick, hopefully. So step 1. If I ever want to graph cosecant, what I'm going to do is graph the sine version, the reciprocal function, reciprocal of cosecant is sine. I will graph that version first, and then I can just kind of use some tricks. As we went around the circle, we got these values for cosecant. So what I did, I just made a special little chart here. I have our x values as we go around the cardinal direction. We already did the cosecant one. We found that it was undefined, 1, undefined, -1, undefined, kept going around. I'm going to put the reciprocal version of it right here next door. This is the sine version. The sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is 0. 3 pi over 2, -1. 2 pi, 0. And we can get some generalizations here. Let's look at this. Whenever sine is 0, the cosecant is undefined, which makes sense, right? Because sine or sine is equal to 1 over cosecant, and cosecant is equal to 1 over sine. Cosecant is 1 over this, undefined. 1 over this, 1. 1 over this, undefined. 1 over this, -1. 1 over this, undefined. So whenever sine is at an inflection point, zeros because we're just talking about the basic version, but whenever it's at an inflection point, that's going to be an asymptote for cosecant. Whenever sine is at a maximum, a 1, that's when cosecant is also going to be a 1. They share points there. And this is going to be the highest this one ever gets. The highest sine ever gets is 1. This is going to be the lowest cosecant ever gets on that little parabola. So maybe sine looks like this. So here's where sine is 1. That would be the bottom of our little parabola-looking thing for cosecant. So a maximum for sine is a minimum for cosecant. And then we keep going around. If it's at 0, that's an asymptote. -1, they share that point. That would be this one down here. At 0, it's undefined. That would be another asymptote. So we can use this idea of reciprocal behaviors. One's going up. Notice, as cosecant's going up, the sine is going down. As sine is going down, cosecant's going up. Sine is asymptote right here. As sine is going down, cosecant's going up. And so on and so forth. So this is our little trick for it. This is called reciprocal behavior, this idea that we're talking about here. So step 1 for our little trick, right? If I want to graph 2 secant, we haven't talked about that, but it's the same as cosine, okay? That's the reciprocal of cosine. If I want to graph y equals 2 secant 3x plus 3, I'm actually going to graph y equals 2 cosine of 3x plus 3. Notice I just flip these around, and then I'm going to use this green one as a tool. So I have this green one I'm going to use. This isn't actually our graph. Remember, we're trying to graph 2 secant 3x plus 3, but we're going to use this as a tool. And the little reciprocal behavior idea, what's happening here is at these nodes, at these points in the middle, these nodes, those are going to be where the asymptotes are for my other graph. So at nodes, I'll put asymptotes. Then wherever I'm at a maximum, that becomes a minimum of our little parabola. If I'm at a minimum, that becomes a maximum of our parabola. So asymptotes at the nodes, in the middle, and then they share those y values at the antinodes, that's the 1s and the -1s. And then we have this idea of reciprocal behaviors. One grows, the other shrinks. As one goes up, the other goes down. So here's what I'm talking about. You'll notice the little green one, I put it as a dotted line to help remind myself it's not actually my graph. I was just using it for help. And eventually, you could get to the point where you won't even need to draw this whole dotted line for your cosine. What you'll just need are those values when we go through and put the dots. Dot, 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 dot. And then remember what the dots are. Okay, those nodes are asymptotes. Maxes become mins become maxes. This is 2 full periods again. It's one of those goofy ones that the book would do. We need 2 parabolas for a full period. So this one and this one combined make 1 full period. This would be a half a period. This is a quarter of a period. This is a quarter of a period. So total, that's 2 full periods. That's the way the book does it. You don't necessarily have to do it that way when I say 2 full periods. If you just gave me this one and this one, and then you gave me this one and this one, a full one of this one, and show me the key values, that would be 2 full periods as well. Okay, so let's recap. Okay, then we'll get some practice there. The recap. If I ever want to graph secant or cosecant, I'm actually going to first graph the reciprocal version of it. If it's secant, I'm going to graph cosine. If it's cosecant, I'm going to graph sine. Then I'm going to use this idea of reciprocal behavior. There's asymptotes at the nodes, those middle ones. They share y values at the antinodes. And then this idea is one goes up, the other goes down. Okay? I have one thing. This was a little like extra practice closing activity. And I'll just do it for you guys that are at home today. It says, given the graph of 2 sine of x plus 2, sketch a graph for 2 cosecant x plus 2. Okay? So the idea is what we just talked about. Let's do the recap. First, graph the reciprocal version. Yeah, I already did that for you. Second, asymptotes at the nodes. Okay, so let's find the nodes. Those are the ones in the middle. Maybe like around here. There'll be an asymptote. Here. Asymptote. There. Asymptote. This is a big one. Asymptote. Looks like I don't see any others. Okay. Next, they share maxes and mins. So at that point, that point, that point, that point, that point, and that point, they're the same. And then finally, reciprocal behavior. As one is going up, the other is going down. And we'll get those little parabola looking things. The blue graph is the cosecant version. That's actually our graph. That's what we're looking for. Okay, so here's the rest of your stamp. Check out the What's Out There page. I'm pretty sure I crossed these out last year, but I've now changed my mind, and I don't want you to cross those out. I want you to do those. So page 422, 1 through 8, 13 through 23, 41, 43, 49, check the what's out there page. It was a long one, but good job sticking with it. Persevere. Be emailing me questions. Peace.